Alright, here we are in 10.3 where we're talking about geometric sequences and series. In this video, I will be using slides that were prepared for Blitzer's Precalculus 3rd edition, and often at the end of these videos I work through some additional practice problems, but today I think we're going to see enough practice right here in these slides, so let's have a look and see what kind of definitions and formulas and problems we can work out here today. The definition of a geometric sequence starts us off with a first term, and then we move from term to term, similar to how we did in an arithmetic sequence, except in an arithmetic sequence, we move from term to term by adding a common difference, remembering that the common difference could be negative, so it would look like we were subtracting a value over and over again in order to move from term to term. But here, in a geometric sequence, we're going to be multiplying a certain number of times in order to reach a particular term. Notice that we have our first term, a sub 1, and in order to arrive at a sub 2, we have multiplied by this number r, which is called the common ratio. So again, in order to get to the second term, we've multiplied by the common ratio once. In order to get to the third term, we've multiplied by the common ratio twice. And to the fourth term, by the common ratio 3 times. So there's always that potential for an off by 1 error. So we have to be careful that we're multiplying by the common ratio the correct number of times. So that's a geometric sequence, a sequence where we move from term to term by multiplying a certain number of times by a common ratio. The common ratio could be greater than 1, could be less than 1, but greater than 0, right? So it could be a fraction that's between 0 and 1, like 1/3. If it were greater than 1, our numbers would keep getting larger and larger. Our common ratio could be negative. We'll see an example of that. But first, let's look at this one. A sub 2 is going to equal a sub 1 times our common ratio 1 time, which will equal 24 times 1/3, which equals 8. A sub 3, one way to get to a sub 3, one way to describe that is we could start with a sub 1 and multiply it by our common ratio 2 times. So we're starting on what I kind of visualize this, right? As I often do. I imagine them like stepping stones. And this is the first stepping stone, a sub 1, which here has a value of 24. And stepping stone number 2, in other words, a sub 2, we arrive at it by taking a step, which requires us to multiply, in this case by 1/3. And then we have to multiply by 1/3 again. That's multiplication, in order to arrive at the third step, a sub 3. So sometimes I'll use that terminology, how many steps do we have to take in order to arrive at a particular term, like a sub 3. And starting on step number 1, in order to get to step number 3, we have to take 2 steps. And you can see that in this very crude diagram here. I give you the best I got. Sometimes it's not pretty, but it's what I have available. Okay, so here I was saying there are a couple of different ways to get there. We can definitely multiply by 1/3 the common ratio 2 times, and after reducing we'll get 8/3. But remember that, as I depicted so beautifully up here, in order to get from step number 2, which was the 8, to the third step, all we have to do is multiply by our common ratio 1 more time. And look at this. If I take the 8 and I multiply it by 1/3, that's an arrow, believe it or not, and multiply it by 1/3 one more time, I get from the 8 to the 8/3. So you can think of it as multiplying over and over again by 1/3. If we multiply by 1/3 again, you can bet that a sub 4 will equal 8 over 9, because 8 over 3 times 1 over 3 equals 8 over 9. So a couple of different ways in order to get to your destination. If you're going a long way, like out to the 40th step or something like that, being mindful that we can use this kind of a format is going to get us there a lot faster. And in fact, here it is. In order to get to a general term or a specific term of a geometric sequence, to get to the nth term, as we say, you can take the first term and multiply it by your common ratio, n minus 1 times. And we saw that n minus 1 in our arithmetic sequence conversation also. The arithmetic sequence, as you might recall, said that a sub n was equal to a sub 1 plus n minus 1, there it is, times the common difference. Okay, if you want to include that in your notes here as a there's this similarity between the two, and that's going to help you remember them. Great. If you're going to do that, if you're going to include this, which is an arithmetic statement, here in our geometric notes, make sure you label this thing as being the general term of a arithmetic sequence. Otherwise, just erase all that, leave it out entirely. I'm taking it out. Get out. Okay, so let's try to use this little formula in order to find a sub 8. We've got a sub 1, we've got r, great, so that should be very straightforward. Eliminate a little background noise there, there's a little traffic. Okay, a sub 8 is equal to a sub 1 times our common ratio to the 8 minus 1 power. So that is 5 times 3 to the 7th power. I'm good, but I'm not that good. 5 times 3 to the power of 7 is 10,935. All right, so I'm going to, as I always do, I just work these problems out like I'm sitting right there with you, working these things out for the first time. I don't have them really pre-worked out because I want you to see the flow of these problems. As a result, the videos get a little bit longer, but you get to see all the work and hear all the thought processes that are part of the solution process. Here in example 2, we need to write the actual formula for the nth term, and then use the formula to find a sub 7. The general version, or the equation for the general term of the geometric sequence, was this one. So let's write that down. A sub n is equal to a sub 1 times our common ratio to the n minus first power. And in order to write this formula, right, so our final answer is going to look a lot like this, except it's going to have numbers in it, except for the left-hand side, it's still going to say a sub n. Do we know what a sub 1 is? We do. It's a 5, so that's going to be easy to drop into place. This n, right, we're writing a formula for the nth term, so these n's are going to stay as they are, but we do need to figure out what our r value is. When we were calculating the common difference in an arithmetic sequence, we would do a sub 2 minus a sub 1. A very similar maneuver here. R is going to equal a sub 2 divided by, wow, that was a mess, a sub 2 divided by a sub 1. So in this problem, we have negative 1 is our second term, 5 is our first term, which means that negative 1/5 is our common ratio. So the formula for a general term in this problem is 5 times negative 1/5 to the n minus first power. And to find a sub 7, Very straightforward. We take the 7, we plug it in for n here, right? Because the question says a sub 7. If that n value is being replaced with a 7, then this one has to be replaced with a 7. So let's go for a sub 7. That's equal to 5 times negative 1/5 to the, if you want to write 7 minus 1 right here, you may. I'm going to go directly to 6. I recommend that you, honestly, let's just do it. Let's write out all the steps. 7 minus 1. That way, when we read these notes again later, we'll know where the 6 came from. So we've got 5 times negative 1 over 5 to the 6th power. Inside these parentheses, we've got a negative value that's being raised to an even power. So we're going to end up with a positive answer because a negative times negative makes a positive. We also have, so it's going to be positive. You don't have to put the plus sign. But this 5 right here is in the numerator. That really says 5 over 1. So there's my 5 in the numerator. In the denominator, I've got 6 multiples of 5. So I've got 5 to the 6th power. There's my 6 multiples of 5. Now this fraction reduces. A 5 from the top and the bottom cancel, and I end up with 1 over 5 to the 5th power. I don't know what that is. Whatever 625 is times 5. Let's just do 5 to the 5th power. We get 3125, so our final answer is 1 over 3125. Writing out some of these steps, if not all of these steps, not trying to do anything in your head, not using any shortcuts, remembering basic properties like what it's like to reduce a fraction where you've got common bases like the 5 in the numerator and the 5 in the denominator, upper minus lower, so an exponent of 1 minus an exponent of 6 gives you an exponent of negative 5. The negative 5 puts you back into the denominator with a positive 5 for the exponent. Those kinds of basic properties, don't forget about those. They're still coming in handy even here. In these printable notes, this is an opportunity to articulate the derivation of this formula. I'm not going to derive this formula for you, but let's have a look at it. This is to find the sum of the first n terms, a specific number of terms of a geometric sequence, S sub n. We're summing n terms. We need to know the first term, a sub 1 is there. We need to know r, the common ratio, and we need to know which term we're trying to find, the nth term. And we're being told that this is applicable where a sub 1 is the first term and r is the common ratio and r does not equal 1. Why can't r equal 1? I can multiply by 1. Yes, you can, but you can't use this formula because then you would have division by 0. That would not go well. If r did equal 1, and you took the first term in your sequence and you multiplied it by 1 in order to get to the next number in your sequence, you'd have the same number over and over again. And that's a different pattern. If you had a 7, and then your next term was a 7, and your next term was a 7, and you knew how many 7s you had, you would just do 7 times n, really, the number of 7s. All right, so that's S sub n, the sum of the first n terms. Let's apply that to this problem. Can I fit both of these on the screen at the same time? Just barely. So remember, we need to know the first term, and I see a sub 1 in example number 3 is going to be the number 4. We are trying to find the sum of the first 11 terms, which means n is going to equal 11. We're not told what our common ratio is, so we're going to have to do that calculation again. All right, let's start. So if you are not using these printable notes and you're writing all this stuff down by hand, maybe you've paused, you've copied down the question, and then let's make sure that we take note that a sub 1 is equal to 4. And actually, I usually like to write down the formula first. Let me do that. The sum of the first n terms is equal to a sub 1, the first term, times 1 minus the common ratio to the nth power. And we're going to divide all of that by 1 minus the common ratio. Great. We just said that a sub 1 is equal to 4. We said that n is equal to 11. And if you're using the pre-printed notes, you could just put your little note up here that that's your n value. And then we need to calculate r. So r is equal to a sub 2 divided by a sub 1. In this case, that's negative 12 divided by 4, which equals negative 3. So we've got our r value, a sub 1, and great. We're good to go. Start plugging stuff in. So s sub, don't write s sub n. We know what n is. It's an 11. Put an 11 in there. S sub 11. Sum of the first 11 terms. Here's my fraction. A sub 1 is a 4 times 1 minus, careful here, negative 3. I'm putting it in parentheses. That's especially important if you're going to be typing this into a calculator, especially a graphing calculator or a 2-line entry scientific calculator. You want to use parentheses maybe more frequently than you think you should, just to make sure that the calculator interprets the information correctly. Plus, I like to be in the habit of anytime I'm substituting one thing for another thing, I like to put the new stuff in parentheses. So here my negative 3 has gone in parentheses. So then we'll start cleaning this up a little bit as best we can. Maybe make it a little bit easier to type into the calculator. This is going to be 1 minus or plus negative 3 to an odd power is still going to be a negative number. And then we're going to be subtracting that negative number. So this is going to turn into addition. So let's put plus, and then I'll jump into my calculator and find out what 3 to the 11th power is. It is 177,147. And then we're going to divide that by, isn't that convenient? Dividing by 4. So the 4s are going to cancel, and your final answer is going to be 177,148. Perfect. Not so bad. Very convenient that the 4s canceled there. If they hadn't, you would have had to do perhaps this initial multiplication by 4, or whatever number this turned out to be, if you could reduce that with the 4 down here, or whatever other number had appeared down there, always try to reduce or simplify before you do your multiplication. Try to make your numbers smaller before you start making them larger. Also, just real quick, this first number was positive. The next number was negative and larger, so to speak. So we had a positive 4, which is only 4 units to the right of 0. And then the negative 12 is 12 units to the left of 0. So you can imagine 0 being on the timeline there, and then you're sort of hopping back and forth across the 0. Excuse me, but each time you jump over the 0, you're going even farther in the other direction. So we started at 0, it's not depicted here, and then we went to 4 as the first term, so a little bit to the right of 0, and then negative 12, so way to the left of 0, and then positive 36, super far to the right of 0, and then negative 108, really far to the left. So we keep doing this where we're jumping over the number 0, but going farther and farther each time. When we get to the 11th term, is that 11th term going to be really, really positive or really, really negative? Our first term was positive. Our third term was positive. I'd be willing to bet you that our 5th term was going to be positive. It seems like our odd numbered terms are positive. So the 11th term is going to be positive, and it's going to be very large, way to the right of 0. So no surprise that our final answer ended up being an awfully large positive number. Adding in these, especially these first few numbers, not hardly even making a dent once we get out to the 11th term and we're working with such a large number that gave us an answer of 177,000 and change. All right, so just a little conversation about keeping our eye on the big picture and making sure that our final answer makes sense with a little bit of pattern recognition in there. This problem is presenting us with a very similar problem actually, but the format is different, of course, because we're using sigma notation or summation notation. We saw that before when we were working with arithmetic sequences, so interesting to see sigma notation here for geometric sequences also. We do still have an index of I, a lower limit, an upper limit for our index, and then we do still have some kind of a formula that's generating our sequence values or our term values. Let's write out at least the first two, let's even write out the first 3 terms. So I've got 1/3 to the, take our I value of 1, plug it in here, add 1 to it, it becomes a 2. Then our next term, we'll have to take an I value of 2, plug it in, and we'll end up with 1/3 to the 2 plus 1 power, which makes a 3, plus 1/3 to the 3 plus 1 power, so to the 4th, plus all the way up to our last index value of 6 going into that exponent position, so 6 plus 1 becoming 7, 1/3 to the 7th power. Okay, what is our, well, what's really happening here? We're summing some terms. Are they terms of a geometric sequence? I'm pretty sure, because we're in the geometric sequence section of this chapter, but we'll talk about how to differentiate geometric, arithmetic, or neither at a later date. How many terms are we going to be summing? If I'm looking at my indices here, or my index values 1 through 6, I think it's pretty safe to say that we're going to be summing the first 6 terms of this sequence. In order to add the first n terms of a geometric sequence, we have a formula for that. We take a sub 1 and we multiply it by 1 minus the common ratio to the nth power, all divided by 1 minus the common ratio. Do we know what a sub 1 is in this problem? We do. It's 1/3 to the 2nd power, so it's going to be 1/9. Do we know what our common ratio is? Not yet, but we know how to calculate it. And do we know what n is? We definitely do. We could have put that in already. It's going to be the 6. So let's do a quick calculation of our r value first. R, as we've heard already a couple of times, is equal to a sub 2 divided by a sub 1 when we're working with a geometric sequence. So that is, now some of you have jumped the gun and written this as 1/27 divided by 1/9, which is okay. And then you can keep change flip. And then you'll reduce, because you're going to have, what do we say, 1/27 divided by 1/9, so you have 1/27 times 9/1, and then you're going to have 9/27, and you have to reduce that fraction. Super, good for you. I'm going to leave this in its kind of raw form as 1/3 to the 3rd power divided by 1/3 to the 2nd power. Notice that we have the same base on the numerator, or in the numerator and denominator. Exponents, how do we simplify this? Upper exponent minus lower exponent, that's a 3 minus a 2. That leaves me with 1/3 to the 1st power, which is 1/3. So either of those two methods would get you there. I chose to save the application of those exponents for later, and as it turned out, I only had to apply an exponent of 1. All right, I'm so fancy. So we've got a ratio, common ratio of 1/3. We know a sub 1, we know r. Great, let's start plugging in values. S sub 6 equals, our first term is 1/9. I'm going to go ahead and apply the exponent there, times 1 minus, our common ratio is 1/3. We're going to have to raise that to the 6th power, and then we'll divide by 1 minus 1/3. This is going to be some interesting arithmetic, and maybe you'll even find this a little, I don't know about entertaining, let's not push it, but maybe clever. I'm going to try to do as little work as possible. Just going to move things around. The 1/9, I'm going to leave it there. 1 minus, now I need 1/3 to the 6th power, but I'm certainly not going to turn that into a decimal. I know that it's 1/3 times 1/3 times 1/3 6 times, right? So my numerators are going to be 1 times 1 times 1 times 1, etc. And the denominators involve 3 6 times. In other words, 3 to the 6th power, which is 729. I just punched that into my calculator. So this fraction turns out to equal 1 over 729. And in my denominator, 1 minus 1/3 is 2/3. All right, inside my parentheses there, that does say 1 over 729, by the way. There you go. In order to do that subtraction, I'll need a common denominator. So I'm going to write this as 1 over 9 times 729 over 729, which certainly equals 1, minus 1 over the 729. And then I'm going to do a keep change flip on the 2/3 from the denominator. Let's multiply that up to here as a 3 over 2. And if you need to pause for a moment and absorb that, that's fine, please do. I think what I'll do next is this 1 over 9 and the 3 over 2, maybe I'll put those next to each other. Those are going to be pretty easy to simplify. 1 over 9 times 3 over 2. So the 3 and the 9 in my next step, those are going to reduce. And then we have to multiply by 729 minus 1 is going to be 728 over, nothing happened with the denominator, that's still 729, which, as you might recall, is made of 6 multiples of 3. Oops, that's quite the equal sign there with my highlighter. Let's reduce anything that we can in an effort to make our numbers smaller before we make them larger. The 3 over 9, let me switch colors. This will reduce, leaving me with a 3 in the denominator. The 728 divided by 2. 2 goes into 7 3 times, carry the 1. 2 goes into 12 6 times, no remainder. 2 goes into 8 4 times. Yes, I have a master's degree in applied mathematics, and I just did long division out loud. But notice, it still works. So I keep using it. Could have used a calculator, but why? I do it in my head. Can we reduce anything else? I don't think so, because 364 is an even number. 729 is made of all 3's. You could try to do the long division. You could try to knock out a 3 from the numerator and denominator, but you'll notice 3 is divisible by 3, 6 is divisible by 3, but 4, you're going to have a remainder of 1, so that's not going to work. Okay, so numerator is 364. Denominator is whatever 729 times another multiple of 3 is. I still have the 729 sitting in my calculator, so all I have to do is hit times 3, enter, and I've got 2187. And that's our final answer. It's an exact answer, not a decimal approximation, and I can be confident that there's no more reducing to be done because I did all of my reducing in the previous step. The 3 over 9 reduced, the 728 over 2 reduced, and then I looked at what I had left. I was mindful of the fact that my 3 in the denominator is an odd number. I remembered that my 729 was made of all 3s. I know where that 729 came from. We created it. There it is. That's the 729 made of all 3s. So keeping those things in mind can increase your confidence a little bit that your final answer is in the most appropriate form, which is usually a reduced form. We want to reduce as much as possible. Applications, that's grown up for word problem. Here we're offered a job that pays $30,000 for the first year, an annual increase of 5% per year beginning in the second year. So your first year on the job, you're going to make 30 grand, and then it goes up at the in your second year. In order to increase your salary by 5%, you will multiply by 1.05. That way you're making 100% of what you made the previous year, and literally an additional 5%. 100% plus 5%, that's 105%. What's 105% as a decimal? 1.05. Okay, we want to know what to expect to earn in our 6th year on the job. Now be careful, this question does not say what will be your total earnings at the end of 6 years. I don't want to know how much money I've made over all 6 years. I just want to know my earnings in the 6th year. Total earnings for all 6 years could be a separate question, but in this case, what we're looking for is a sub, I'm going to write a sub n, but what we're looking for is a sub 6, a specific term, a specific year's worth of income. Remember that a sub n is equal to a sub 1, our first term, times our common ratio to the n minus 1 power. Do we know what a sub 1 is in this problem? It's 30,000, the amount of money that we made in our first year. Do we know what the common ratio is? Do we know what we're going to be multiplying by over and over again? Definitely. It's the 1.05. And do we know what our n value is? Yes, we want our salary in the 6th year, so we're good to go. If you want to label those things, you can. For those of you with the printable notes, we could call this a sub 1. You could get an r in there somehow. And 6th year on the job, this is going to be our n value is a 6. Okay, so a sub 6 equals a sub 1, that's 30,000. Our common ratio, 1.05 to the power of 6 minus 1. The only thing I can do in my head is the 6 minus 1. After that, I'm going into the calculator. In a graphing calculator, this is nice because you can just type it in from left to right. If you're using a single line entry scientific calculator, you should probably type in 1.05 to the 5th power equals, get whatever gnarly decimal that is, leave it right there on your screen, and then hit times 30,000 equals. If you're using a 4-function calculator, you can still do this. 1.05 times, 1.05 times, just make sure that you multiply only 5 times. And then after you type in that last 1.05, you can hit times, type in the 30,000, and hit equals. That'll get you there. In my grapher, I'm going to type in 30,000 times 1.05 to the power of 5, enter, and I got $38,288.45. It was actually 0.446, so I'm going to round up. I'll write that down for us. $38,288.45. Nice, not a bad word problem. Just have to know what the most appropriate formula is to use and being able to identify the values that are going into the different locations in the formula. If we wanted to add up all 6 years worth of our salary, we would be using the S as in sum, the summation formula, And we would only need the same values, a sub 1, r, and n. You could plug them in. You'll have to be careful using that formula because it's a fraction, but still very doable. And maybe finally is this conversation about annuities. Oh, and we're going to talk about infinite geometric series. Okay, so an annuity is an investment vehicle that you can pay into. P, when we're talking about financial stuff, usually stands for principal. So this is not just making a deposit into a savings account or a stock or something like that where you're going to be doing compound interest. P is the deposit made at the end of each compounding period. For example, in my job, I make contributions to a retirement savings plan. And my contributions that I make are a percentage of my income, but I make the contribution every time I get a paycheck. So every 2 weeks, I'm adding to the amount that's growing. So in the example problem that we're going to see on the next page, the contributions to that annuity are going to be made annually, which means we're only making them one time per year. In my case, because I'm making my contributions bi-weekly, every 2 weeks, I'm going to be contributing not one time per year, but 26 times per year. So this problem for me, or the next problem we're going to do for me, would be a little bit different. But my p-value would be the same. It's some small percentage of my income every 2 weeks. A is our final value. R is the annual interest rate. Annual interest rate. We're going to divide that by n, which is going to make it a smaller number. Well, for me, it gets to be a smaller number. And t is measured in years, so be careful that you're using the right units. That's n times t up there. T is measured in years. Okay, let's see what this problem looks like. Let's label our variable values. So we have the amount of money that we're going to be depositing over and over again. So at the end of each year is $2,500. So that's going to be our p value. And if you're taking notes by hand, you're just writing down p equals 2,500. We're making that deposit into an IRA, an individual retirement account, I believe IRA stands for, at the end of each year. What that tells me is that n is equal to 1. The number of contributions per year, and it's the number of compoundings per year for the next 40 years. Isn't that scary? That's our t value. If the interest rate is 9%, so 9% is going to be our interest rate, but as a decimal, it's going to be 0.09 compounded annually. So this is a reiteration of the fact that our n value is 1. Find the value. So we're looking for capital A, as we saw in our formula. So let's try it. Capital A equals $2,500. Using my parentheses, 1 plus my interest rate, 0.09, divided by, in this case, since I'm compounding annually, my denominator there is only a 1. We're raising that to the power of 1 times 40. This digital pen's pretty accurate, but that does say 1 times 40. Hopefully you can read that. Minus 1. Close, all divided by interest rate 0.09 divided by 1 equals. If you have even a 2-line entry scientific calculator, you can pretty much type this thing in from left to right. I think I would do one little bit of arithmetic using pencil and paper first. I would write this maybe as, knowing that the 0.09 divided by 1 is still 0.09, that's kind of nice. I would probably do 2,500 divided by my 0.09 So because multiplication and division have the same priority level in PEMDAS, I can do those in whichever order I want. Multiplication, division, I can shuffle them around. So I'm going to do that division first, and then I'm going to multiply by. Now in these parentheses, this says 1 plus, and then 0.09 divided by 1 again is still 0.09. So what's 1 plus 0.09? It's 1.09. And we're going to be raising that to the power of, well, this arithmetic, I can do that in my head. That's going to be a 40. And then I do still have to do minus 1. Again, this is, you can see how much more compact it is. So this is maybe even easier for you to type into the calculator from left to right. 2500 divided by 0.09. Enter, or equals if you want. Now you've got a number on your screen. You can hit times. And this is when it gets a little bit tricky. After you hit times, you're going to need to use parentheses. And in fact, you're going to, yeah, you could use parentheses once. And then you'll type in your 1.09 to the 40th power. Depending on your calculator, you may or may not have to hit enter again, and then the minus 1, and then close your parentheses. A better bet would be, especially if you're using a single line entry scientific calculator, I'll write out the order that I would recommend you type this in. But if you're using a grapher, just type this thing in. I'll show you how I would type it in on my graphing calculator. Single line scientific calculator. I would type this in first, and you're going to get some lousy looking decimal on your screen. I'll tell you what you should get. You should get 31.409 blah blah blah. Then on your scientific calculator, or on your grapher if you want, whatever. This works on all the calculators. Then hit minus 1 equals. Now it's 30.409 blah 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 blah. So I would do this second, and then you can do these in whichever order you want. You could hit times 2500 and then divided by 0.09, or vice versa. If you want to do the times 2500, you should then have 76,023.55, and then divide by 0.09 equals, and you get your final answer, which is the same answer I got when I typed the entire thing in all in one go. I got $844,706 and 0.1126. So since it's 0.112, I rounded down and left it as 11 cents. And that is the amount of money that you should have in your IRA at the end of those 40 years. I'll share something with you that I learned when I first got my job at the university where I teach. When did I get my job there? 7 years ago. It's 2020, so it was like 2013 when I got hired on as full-time faculty. And I met with a financial advisor because I have this retirement savings plan through the university. And we're talking about my income and my lifestyle. And he said, listen, when it comes time for you many years from now to retire, I got to tell you, you're running a little behind, because in order to, based on all the averages, in order for the payout from your retirement plan to be giving you enough money to sustain the kind of lifestyle that you like to lead, you should have approximately $2.5 million in your total retirement savings, whether you've got multiple avenues for retirement savings or only one. 2.5 million. This person putting $2,500 in annually with a 9% growth rate, which is hard to come by, is going to only have $844,000. You should look up and see what the numbers are for the average lifetime earnings of a person with a bachelor's degree, average lifetime earnings of a person with a master's degree, or a PhD, or do some research that's field specific, right? If you're in the hard sciences, if you're in tech, if you're in the medical community, if you're in the legal system, legal community, try to figure out an average lifetime income. The last time I had this conversation, the average lifetime income of a person with a bachelor's degree was like $900,000. And with a master's, it was 1.1 million. And with a PhD, it was 1.5 million. And I thought, oh, great. In my entire lifetime, I'm not even going to earn the amount of money that I need to have saved by the time I hit retirement. So, quick, start saving. Live below your means, save your heart out, and make sure that you don't have to be working when you hit retirement age. You want to be relaxing as soon as humanly possible. All right, maybe the last topic. I can't even remember. I talk too much. Geometric series. Oh, this is the infinite geometric series, and we're only going to be using this formula to find the sum of an infinite geometric series if the common ratio is between negative and positive 1. If your common ratio is anywhere outside of that, then your term values will get too large, either in the positive direction or the negative direction, and you won't be able to add them up. It'll either end up being positive infinity or negative infinity, or you won't be able to tell which. In fact, you won't be able to tell which. It's just not doable. Remember when we were hopping across the number 0, getting even bigger in the positive direction and then even bigger in the negative direction? Adding those up on your way out to infinity, it's not going to go well. So we'll stay with common ratio values that are between negative and positive 1. This is a very compact formula. Awesome. We need to know what a sub 1 is. In this example problem, we know what it is. We have to figure out what our common ratio is. R is equal to a sub 2 divided by a sub 1. In this case, that's 1/4 divided by 1, which is 1/4, which is good because 1/4 is between negative and positive 1. So we're good to go on the formula. If you want to put a little note into your notes saying, we can use the formula above because 1/4 is between negative and positive 1. Maybe you should have that in your notes. I'm not going to write that down, but pause and write that down if you want to. Then we'll go into the formula. The sum, I don't need to have a little subscript here because I'm going out to infinity. You want to put a little infinity symbol down here, that's fine. I don't think that that's typical to do that. A sub 1 we said is 1/4. No, it's not, it's a 1. And then our denominator is 1 minus our common ratio of 1/4. That's equal to 1 divided by 3/4. Because if you have $1 and you take away 1/4, you have 3/4 in your pocket. In other words, 3/4. You could do a little keep, change, flip on this thing. Instead of dividing by 3/4, multiply by 4/3, and your final answer in this problem is positive 4/3. Interesting to think that you can add up all infinitely many of these fractions, and you're going to end up with such a nice clean number as 4/3. Oh, and that's it. Those are the end of our notes for 10.3. As you can see at the bottom of the screen, our next topic is mathematical induction. I will never forget learning that for the first time, and I always take great pride in teaching it to you because it is a very unique topic, and I look forward to sharing mathematical induction with you in the next section. Until then, be well, and thank you so much.